The Moon is an astronomical body that orbits Earth as its only natural satellite. It is the fifth largest satellite in the solar system and the largest among planetary satellites relative to the size of the planet that it orbits. The Moon is, after Jupiter's satellite Io, the second densest satellite in the solar system, among those whose densities are known. The Moon is thought to have formed about 4.51 billion years ago, not long after Earth. The most widely accepted explanation is that the Moon formed from the debris left over after a giant impact between Earth and a Mars-sized body called Theia. New research of moon rocks, although not rejecting the Theia hypothesis, suggests that the Moon may be older than previously thought. The Moon is in synchronous rotation with Earth, and thus always shows the same side to Earth, the near side. The near side is marked by dark volcanic maria that fill the spaces between the bright ancient crustal highlands and the prominent impact craters. After the Sun, the Moon is the second brightest regularly visible celestial object in Earth's sky. Its surface is actually dark, although compared to the night sky it appears very bright, with a reflectance just slightly higher than that of worn asphalt. Its gravitational influence produces the ocean tides, body tides, and the slight lengthening of the day. The Moon's average orbital distance is 384,402 kilometers, 238,856 miles, or 1.28 light seconds. This is about 30 times the diameter of Earth. The Moon's apparent size in the sky is almost the same as that of the Sun, since the star is about 400 times the lunar distance and diameter. Therefore, the Moon covers the Sun nearly precisely during a total solar eclipse. This matching of apparent visual size will not continue in the far future because the Moon's distance from Earth is gradually increasing. The Moon was first reached in September 1959 by the Soviet Union's Luna 2, an unmanned spacecraft, followed by the first successful soft landing by Luna 9 in 1966. The United States NASA Apollo program achieved the only manned lunar missions to date, beginning with the first manned orbital mission by Apollo 8 in 1968, and 6 manned landings between 1969 and 1972, with the first being Apollo 11 in July 1969. These missions returned lunar rocks which have been used to develop a geological understanding of the Moon's origin, internal structure, and the Moon's later history. Since the 1972 Apollo 17 mission, the Moon has been visited only by unmanned spacecraft. Both the Moon's natural prominence in the earthly sky and its regular cycle of phases, as seen from Earth, have provided cultural references and influences for human societies and cultures since time immemorial. Such cultural influences can be found in language, lunar calendar systems, art, and mythology. The Moon formed 4.51 billion years ago, some 60 million years after the origin of the solar system. Several forming mechanisms have been proposed, including the fission of the Moon from Earth's crust through centrifugal force, which would require too great an initial spin of Earth, the gravitational capture of a preformed Moon, which would require an unfeasibly extended atmosphere of Earth to dissipate the energy of the passing Moon, and the co-formation of Earth and the Moon together in the primordial accretion disk, which does not explain the depletion of metals in the Moon. These hypotheses also cannot account for the high angular momentum of the Earth-Moon system. The prevailing hypothesis is that the Earth-Moon system formed after an impact of a Mars-sized body, named Theia, with the proto-Earth giant impact. The impact blasted material into Earth's orbit, and then the material accreted and formed the Moon. The Moon's far side has a crust that is 50 kilometers thicker than that of the near side. This is thought to be because the Moon fused from two different bodies. This hypothesis, although not perfect, perhaps best explains the evidence. 18 months prior to an October 1984 conference on lunar origins, Bill Hartmann, Roger Phillips, and Jeff Taylor challenged fellow lunar scientists. You have 18 months. Go back to your Apollo data. Go back to your computer. Do whatever you have to, but make up your mind. Don't come to our conference unless you have something to say about the Moon's birth. At the 1984 conference at Kona, Hawaii, the giant impact hypothesis emerged as the most consensual theory. Before the conference, there were partisans of the three theories, plus a few people who were starting to take the giant impact seriously. And there was a huge apathetic middle who didn't think the debate would ever be resolved. Afterward, there were essentially only two groups: the giant impact camp and the agnostics. Giant impacts are thought to have been common in the early solar system. Computer simulations of giant impacts have produced results that are consistent with the mass of the lunar core and the angular momentum of the Earth-Moon system. These simulations also show that most of the Moon derived from the impactor, rather than the proto-Earth. However, more recent simulations suggest a larger fraction of the Moon derived from the proto-Earth. Are the bodies of the inner solar system such as Mars and Vesta have, according to meteorites from them, very different oxygen and tungsten isotopic compositions compared to Earth? However, Earth and the Moon have nearly identical isotopic compositions. The isotopic equalization of the Earth-Moon system might be explained by the post-impact mixing of the vaporized material that formed the two, although this is debated. The impact released a lot of energy, and then the released material reaccreted into the Earth-Moon system. This would have melted the outer shell of Earth, and thus formed a magma ocean. Similarly, the newly formed Moon would also have been affected and had its own lunar magma ocean. Its depth is estimated from about 500 kilometers to 1,737 kilometers. While the giant impact hypothesis might explain many lines of evidence, some questions are still unresolved. most of which involve the Moon's composition. In 2001, a team at the Carnegie Institute of Washington reported the most precise measurement of the isotropic signatures of lunar rocks. To their surprise, the rocks from the Apollo program had the same isotropic signature as rocks from Earth. However, they differed from almost all other bodies in the solar system. Indeed, this observation was unexpected, because most of the material that formed the Moon was thought to come from Theia, and it was announced in 2007 that there was less than a 1% chance that Theia and Earth have identical isotropic signatures. Other Apollo lunar samples had in 2012 the same titanium isotopes composition as Earth, which conflicts with what is expected if the Moon formed far from Earth or is derived from Theia. These discrepancies may be explained by variations of the giant impact hypothesis. The Moon is a very slightly scalene ellipsoid due to tidal stretching, with its long axis displaced 30 degrees from facing the Earth, due to gravitational anomalies from impact basins. Its shape is more elongated than current tidal forces can account for. This fossil bulge indicates that the Moon solidified when it orbited at half its current distance to the Earth, and that it is now too cold for its shape to adjust to its orbit. The Moon is a differentiated body. It has a geochemically distinct crust, mantle, and core. The Moon has a solid iron-rich inner core, with a radius possibly as small as 240 kilometers, and a fluid outer core primarily made of liquid iron, with a radius of roughly 300 kilometers. Around the core is a partially molten boundary layer, with a radius of about 500 kilometers. This structure is thought to have developed through the fractional crystallization of a global magma ocean shortly after the Moon's formation 4.5 billion years ago. Crystallization of this magma ocean would have created a mafic mantle from the precipitation and sinking of the minerals olivine, clinopyroxene, and orthopyroxene. After about 3/4 of the magma ocean had crystallized, lower density plagioclase minerals could form and float into a crust atop. The final liquids to crystallize would have been initially sandwiched between the crust and mantle, with a high abundance of incompatible and heat-producing elements. Consistent with this perspective, geochemical mapping made from orbit suggests the crust of mostly anorthosite. The Moon rock samples of the flood lavas that erupted onto the surface from partial melting in the mantle confirm the mafic mantle composition, which is more iron-rich than that of Earth. The crust is on average about 50 kilometers thick. The Moon is the second densest satellite in the solar system, after Io. However, the inner core of the Moon is small, with a radius of about 350 kilometers or less, around 20% of the radius of the Moon. Its composition is not well understood, but is probably metallic iron alloyed, with a small amount of sulfur and nickel. Analyses of the Moon's time variable rotation suggest that it is at least partly molten. The topography of the Moon has been measured with laser altimetry and stereo image analysis. Its most visible topographic feature is the giant far-side South Pole Aitken Basin, some 2,240 kilometers in diameter. The largest crater on the Moon, and the second largest confirmed impact crater in the Solar System. At 13 kilometers deep, its floor is the lowest point on the surface of the Moon. The highest elevations of the surface are located directly to the northeast, and it has been suggested might have been thickened by the oblique formation impact of the South Pole Aitken Basin. Other large impact basins such as Imbrium, Serenitatis, Chrysium, Smythii, and Oriental also possess regionally low elevations and elevated rims. The far side of the lunar surface is on average about 1.9 kilometers higher than that of the near side. The discovery of fault scarp cliffs by the Lunar Reconnaissance Orbiter suggests that the Moon has shrunk within the past billion years by about 90 meters. Similar shrinkage features exist on Mercury. A recent study of over 12,000 images from the orbiter has observed that Mare Frigoris near the North Pole, a vast basin assumed to be geologically dead, has been cracking and shifting. Since the Moon doesn't have tectonic plates, its tectonic activity is slow and cracks develop as it loses heat over the years. The dark and relatively featureless lunar plains, clearly seen with the naked eye, are cold seas, as they were once believed to be filled with water. They are now known to be vast solidified pools of ancient basaltic lava. Although similar to terrestrial basalts, lunar basalts have more iron and no minerals altered by water. The majority of these lavas erupted or flowed into the depressions associated with impact basins. Several geologic provinces containing shield volcanoes and volcanic domes are found within the near-side seas. Almost all Maria are on the near side of the Moon, and cover 31% of the surface of the near side, compared with 2% of the far side. This is thought to be due to a concentration of heat-producing elements under the crust on the near side, seen on geochemical maps obtained by Lunar Prospector's gamma-ray spectrometer, which would have caused the underlying mantle to heat up, partially melt, rise to the surface and erupt. Most of the Moon's mare basalts erupted during the Imbrian period, 3.0 to 3.5 billion years ago, although some radiometrically dated samples are as old as 4.2 billion years. Until recently, the youngest eruptions, dated by crater counting, appeared to have been only 1.2 billion years ago. In 2006, a study of Ina, a tiny depression in Lacus Felicitatis, found jagged, relatively dust-free features that, because of the lack of erosion by infalling debris, appeared to be only 2 million years old. Moonquakes and releases of gas also indicate some continued lunar activity. In 2014, NASA announced widespread evidence of young lunar volcanism at 70 irregular mare patches identified by the Lunar Reconnaissance Orbiter, some less than 50 million years old. This raises the possibility of a much warmer lunar mantle than previously believed, at least on the near side where the deep crust is substantially warmer because of the greater concentration of radioactive elements. Just prior to this, evidence has been presented for 2 to 10 million years younger basaltic volcanism inside Lowell Crater, Oriental Basin, located in the transition zone between the near and far sides of the Moon. An initially hotter mantle and all local enrichment of heat-producing elements in the mantle could be responsible for prolonged activities also on the far side, in the Oriental Basin. The lighter-colored regions of the Moon are called terrae, or more commonly highlands, because they are higher than most maria. They have been radiometrically dated to having formed 4.4 billion years ago, and may represent plagioclase cumulates of the lunar magma ocean. In contrast to Earth, no major lunar mountains are believed to have formed as a result of tectonic events. The concentration of maria on the near side likely reflects the substantially thicker crust of the highlands of the far side, which may have formed in a slow-velocity impact of a second moon of Earth a few tens of millions of years after their formation. The other major geologic process that has affected the Moon's surface is impact cratering, with craters formed when asteroids and comets collide with the lunar surface. There are estimated to be roughly 300,000 craters wider than 1 kilometer on the Moon's near side alone. The lunar geologic timescale is based on the most prominent impact events, including Nectaris, Imbrium, and Oriental, structures characterized by multiple rings of uplifted material between hundreds and thousands of kilometers in diameter and associated with a broad apron of ejecta deposits that form a regional stratigraphic horizon. The lack of an atmosphere, weather and recent geological processes mean that many of these craters are well preserved. Although only a few multi-ring basins have been definitively dated, they are useful for assigning relative ages. Because impact craters accumulate at a nearly constant rate, counting the number of craters per unit area can be used to estimate the age of the surface. The radiometric ages of impact melted rocks collected during the Apollo missions cluster between 3.8 and 4.1 billion years old. This has been used to propose a late heavy bombardment of impacts. Blanketed on top of the Moon's crust is a highly comminuted, broken into ever smaller particles, and impact-gardened surface layer, called regolith, formed by impact processes. The finer regolith, the lunar soil of silicon dioxide glass, has a texture resembling snow, and a scent resembling spent gunpowder. The regolith of older surfaces is generally thicker than for younger surfaces. It varies in thickness from 10 to 20 kilometers in the highlands and 3 to 5 kilometers in the maria. Beneath the finely comminuted regolith layer is the megaregolith, a layer of highly fractured bedrock, many kilometers thick. Comparison of higher resolution images obtained by the Lunar Reconnaissance Orbiter has shown a contemporary crater production rate significantly higher than previously estimated. A secondary cratering process caused by distal ejecta is thought to churn the top 2 centimeters of regolith 100 times more quickly than previous models suggested, on a timescale of 81,000 years. Lunar swirls are enigmatic features found across the Moon's surface. They are characterized by a high albedo, appear optically immature, the optical characteristics of a relatively young regolith, and have often a sinuous shape. Their shape is often accentuated by low albedo regions that wind between the bright swirls. Liquid water cannot persist on the lunar surface. When exposed to solar radiation, water quickly decomposes through a process known as photodissociation and is lost to space. However, since the 1960s, scientists have hypothesized that water ice may be deposited by impacting comets or possibly produced by the reaction of oxygen-rich lunar rocks and hydrogen from solar wind, leaving traces of water which could possibly persist in cold, permanently shadowed craters at either pole on the Moon. Computer simulations suggest that up to 14,000 square kilometers of the surface may be in permanent shadow. The presence of usable quantities of water on the Moon is an important factor in rendering lunar habitation as a cost-effective plan. The alternative of transporting water from Earth would be prohibitively expensive. In years since, signatures of water have been found to exist on the lunar surface. In 1994, the B-static radar experiment located on the Clementine spacecraft indicated the existence of small, frozen pockets of water close to the surface. However, later radar observations by Arecibo suggest these findings may rather be rocks ejected from young impact craters. In 1998, the neutron spectrometer on the Lunar Prospector spacecraft showed that high concentrations of hydrogen are present in the first meter of depth in the regolith near the polar regions. Volcanic lava beads brought back to Earth aboard Apollo 15 showed small amounts of water in their interior. The 2008 Chandrayaan-1 spacecraft has since confirmed the existence of surface water ice using the onboard Moon Mineralogy Mapper. The spectrometer observed absorption lines common to hydroxyl in reflected sunlight, providing evidence of large quantities of water ice on the lunar surface. The spacecraft showed that concentrations may possibly be as high as 1,000 parts per million. Using the mapper's reflectance spectra, indirect lighting of areas in shadow confirmed water ice within 20 degrees latitude of both poles in 2018. In 2009, LaCrosse sent a 2,300 kilograms impactor into a permanently shadowed polar crater and detected at least 100 kilograms of water in a plume of ejected material. Another examination of the LaCrosse data showed the amount of detected water to be closer to 150 kilograms. In May 2011, 615 to 1,410 parts per million water in melt inclusions in lunar sample 74,220 was reported. The famous high titanium of volcanic origin collected during the Apollo 17 mission in 1972 The inclusions were formed during explosive eruptions on the Moon approximately 3.7 billion years ago. This concentration is comparable with that of magma in Earth's upper mantle. Although of considerable selenological interest, this announcement affords little comfort to would-be lunar colonists. The sample originated many kilometers below the surface, and the inclusions are so difficult to access that it took 39 years to find them. With a state-of-the-art ion microprobe instrument analysis of the findings of the Moon Mineralogy Mapper, M3, revealed in August 2018 for the first time definitive evidence for water ice on the lunar surface. The data revealed the distinct reflective signatures of water ice, as opposed to dust and other reflective substances. The ice deposits were found on the north and south poles, although it is more abundant in the south, where water is trapped in permanently shadowed craters and crevices, allowing it to persist as ice on the surface since they are shielded from the sun. The gravitational field of the Moon has been measured through tracking the Doppler shift of radio signals emitted by orbiting spacecraft. The main lunar gravity features are mascons, large positive gravitational anomalies associated with some of the giant impact basins, partly caused by the dense mare basaltic lava flows that fill those basins. The anomalies greatly influence the orbit of spacecraft about the Moon. There are some puzzles. Lava flows by themselves cannot explain all of the gravitational signature, and some mascons exist that are not linked to mere volcanism. The Moon has an external magnetic field of about 1 to 100 nanoteslus, less than 1/100th that of Earth. The Moon does not currently have a global dipolar magnetic field and only has crustal magnetization, likely acquired early in its history when a dynamo was still operating. Theoretically, some of the remnant magnetization may originate from transient magnetic fields generated during large impacts through the expansion of plasma clouds. These clouds are generated during large impacts in an ambient magnetic field. This is supported by the location of the largest crustal magnetizations situated near the antipodes of the giant impact basins. The Moon has an atmosphere so tenuous as to be nearly vacuum, with a total mass of less than 10 tons. Its sources include outgassing and sputtering, a product of the bombardment of lunar soil by solar wind ions. Elements that have been detected include sodium and potassium, produced by sputtering, also found in the atmospheres of Mercury and Io, helium-4 and neon from the solar wind, and argon-40, radon-222, and polonium-210, August, after their creation by radioactive decay within the crust and mantle. The absence of such neutral species, atoms or molecules, as oxygen, nitrogen, carbon, hydrogen and magnesium, which are present in the regolith, is not understood. Water vapor has been detected by Chandrayaan-1 and found to vary with latitude, with a maximum at 60 to 70 degrees. It is possibly generated from the sublimation of water ice in the regolith. These gases either return into the regolith because of the Moon's gravity or are lost to space, either through solar radiation pressure or, if they are ionized, by being swept away by the solar wind's magnetic field. A permanent asymmetric moon dust cloud exists around the Moon, created by small particles from comets. Estimates are 5 tons of comet particles strike the Moon's surface every 24 hours. The particles striking the Moon's surface eject moon dust above the Moon. The dust stays above the Moon approximately 10 minutes, taking 5 minutes to rise and 5 minutes to fall. On average, 120 kilograms of dust are present above the Moon, rising to 100 kilometers above the surface. The dust measurements were made by Lady's Lunar Dust Experiment, LDEX, between 20 and 100 kilometers above the surface, during a 6-month period. LDEX detected an average of 0.3 micrometer moon dust particle each minute. Dust particle counts peaked during the Geminid, Quadrantid, Northern Taurid, and Omicron Centaurid meteor showers, when the Earth and Moon pass through comet debris. The cloud is asymmetric, more dense near the boundary between the Moon's day side and night side. In October 2017, NASA scientists at the Marshall Space Flight Center and the Lunar and Planetary Institute in Houston announced their finding, based on studies of Moon magma samples retrieved by the Apollo missions, that the Moon had once possessed a relatively thick atmosphere for a period of 70 million years, between 3 and 4 billion years ago. This atmosphere, sourced from gases ejected from lunar volcanic eruptions, was twice the thickness of that of present-day Mars. The ancient lunar atmosphere was eventually stripped away by solar winds and dissipated into space. The Moon's axial tilt, with respect to the ecliptic, is only 1.5424 degrees, much less than the 23.44 degrees of Earth. Because of this, the Moon's solar illumination varies much less, with season and topographical details play a crucial role in seasonal effects. From images taken by Clementine in 1994, it appears that 4 mountainous regions on the rim of pre-crater at the Moon's north pole may remain illuminated for the entire lunar day, creating peaks of eternal light. No such regions exist at the South Pole. Similarly, there are places that remain in permanent shadow at the bottoms of many polar craters, and these craters of eternal darkness are extremely cold. Lunar Reconnaissance Orbiter measured the lowest summer temperatures in craters at the southern pole at -238 degrees Celsius, -397 degrees Fahrenheit, and just -247 degrees Celsius, -413 degrees Fahrenheit, close to the winter solstice in North Polar Hermite Crater. This is the coldest temperature in the solar system ever measured by a spacecraft, colder even than the surface of Pluto. Average temperatures of the Moon's surface are reported, but temperatures of different areas will vary greatly depending upon whether they are in sunlight or shadow. The Moon makes a complete orbit around Earth, with respect to the fixed stars, about once every 27.3 days, its sidereal period. However, because Earth is moving in its orbit around the Sun at the same time, it takes slightly longer for the Moon to show the same phase to Earth, which is about 29.5 days, its synodic period. Unlike most satellites of other planets, the Moon orbits closer to the ecliptic plane than to the planet's equatorial plane. The Moon's orbit is subtly perturbed by the Sun and Earth in many small, complex and interacting ways. For example, the plane of the Moon's orbit gradually rotates once every 18.61 years, which affects other aspects of lunar motion. These follow-on effects are mathematically described by Cassini's laws. The Moon is exceptionally large relative to Earth. Its diameter is more than a quarter and its mass is 1/81 of Earth's. It is the largest moon in the solar system relative to the size of its planet, though Charon is larger relative to the dwarf planet Pluto at 1/9 Pluto's mass. The Earth and the Moon's barycenter, their common center of mass, is located 1,700 kilometers, about a quarter of Earth's radius, beneath Earth's surface. The Earth revolves around the Earth-Moon barycenter once a sidereal month, with 1/81 the speed of the Moon, or about 12.5 meters per second. This motion is superimposed on a much larger revolution of the Earth around the Sun at a speed of about 30 kilometers per second. The surface area of the Moon is slightly less than the areas of North and South America combined. The Moon is in synchronous rotation. As it orbits Earth, it rotates about its axis in about the same time it takes to orbit Earth. This results in it always keeping nearly the same face turned towards Earth. However, because of the effect of libration, about 59% of the Moon's surface can actually be seen from Earth. The side of the Moon that faces Earth is called the near side, and the opposite the far side. The far side is often inaccurately called the dark side, but it is in fact illuminated as often as the near side, once every 29.5 Earth days. During new moon, the near side is dark. The Moon had once rotated at a faster rate, but early in its history, its rotation slowed and became tidally locked in this orientation, as a result of frictional effects associated with tidal deformations caused by Earth. With time, the energy of rotation of the Moon on its axis was dissipated as heat, until there was no rotation of the Moon relative to Earth. In 2016, planetary scientists, using data collected on the much earlier NASA Lunar Prospector mission, found two hydrogen-rich areas on opposite sides of the Moon, probably in the form of water ice. It is speculated that these patches were the poles of the Moon billions of years ago, before it was tidally locked to Earth. The Moon has an exceptionally low albedo, giving it a reflectance that is slightly brighter than that of worn asphalt. Despite this, it is the brightest object in the sky. after the Sunday. This is due partly to the brightness enhancement of the opposition surge. The moon at quarter phase is only 1/10 as bright, rather than half as bright, as at full moon. Additionally, color constancy in the visual system recalibrates the relations between the colors of an object and its surroundings. And because the surrounding sky is comparatively dark, the sunlit moon is perceived as a bright object. The edges of the full moon seem as bright as the center, without limb darkening, because of the reflective properties of lunar soil, which retroflects light more towards the sun than in other directions. The moon does appear larger when close to the horizon, but this is a purely psychological effect, known as the moon illusion, first described in the 7th century BC. The full moon's angular diameter is about 0.52 degrees on average in the sky, roughly the same apparent size as the Sun. The moon's highest altitude at culmination varies by its phase and time of year. The full moon is highest in the sky during winter for each hemisphere. The 18.61-year nodal cycle has an influence on lunar standstill. When the ascending node of the lunar orbit is in the vernal equinox, the lunar declination can reach up to plus or minus 28 degrees each month. This means the moon can pass overhead if viewed from latitudes up to 28 degrees north or south of the equator, instead of only 18 degrees. The orientation of the moon's crescent also depends on the latitude of the viewing location. An observer in the tropics can see a smile-shaped crescent moon. The moon is visible for 2 weeks every 27.3 days at the North and South Poles. Zooplankton in the Arctic use moonlight when the sun is below the horizon for months on end. The distance between the moon and Earth varies from around 356,400 kilometers, 221,500 miles, to 406,700 kilometers, 252,700 miles, at perigee, closest, and apogee, farthest, respectively. On the 14th of November 2016, it was closer to Earth when at full phase than it has been since 1948, 14% closer than its farthest position in apogee. The gravitational attraction that masses have for one another decreases inversely with the square of the distance of those masses from each other. As a result, the slightly greater attraction that the moon has for the side of Earth closest to the moon, as compared to the part of the Earth opposite the moon, results in tidal forces. Tidal forces affect both the Earth's crust and oceans. The most obvious effect of tidal forces is to cause two bulges in the Earth's oceans, one on the side facing the moon, and the other on the side opposite. This results in elevated sea levels, called ocean tides. As the Earth spins on its axis, one of the ocean bulges, high tide, is held in place under the moon, while another such tide is opposite. As a result, there are two high tides and 2 low tides in about 24 hours. Since the Moon is orbiting the Earth in the same direction of the Earth's rotation, the high tides occur about every 12 hours and 25 minutes. The 25 minutes is due to the Moon's time to orbit the Earth. The Sun has the same tidal effect on the Earth, but its forces of attraction are only 40% that of the Moon's. The Sun's and Moon's interplay is responsible for spring and neap tides. If the Earth were a water world, one with no continents, it would produce a tide of only 1 meter, and that tide would be very predictable. But the ocean tides are greatly modified by other effects. The frictional coupling of water to Earth's rotation through the ocean floors, the inertia of water's movement, ocean basins that grow shallower near land, the sloshing of water between different ocean basins. As a result, the timing of the tides at most points on the Earth is a product of observations that are explained incidentally by theory. While gravitation causes acceleration and movement of the Earth's fluid oceans, gravitational coupling between the Moon and Earth's solid body is mostly elastic and plastic. The result is a further tidal effect of the Moon on the Earth that causes a bulge of the solid portion of the Earth nearest the Moon that acts as a torque in opposition to the Earth's rotation. This drains angular momentum and rotational kinetic energy from Earth's spin, slowing the Earth's rotation. That angular momentum, lost from the Earth, is transferred to the Moon in a process confusingly known as tidal acceleration, which lifts the Moon into a higher orbit and results in its lower orbital speed about the Earth. Thus the distance between Earth and Moon is increasing, and the Earth's spin is slowing in reaction. Measurements from laser reflectors left during the Apollo missions' lunar ranging experiments have found that the Moon's distance increases by 38 millimeters per year, roughly the rate at which human fingernails grow. Atomic clocks also show that Earth's day lengthens by about 15 microseconds every year, slowly increasing the rate at which UTC is adjusted by leap seconds. Left to run its course, this tidal drag would continue until the spin of Earth and the orbital period of the Moon matched, creating mutual tidal locking between the two. As a result, the Moon would be suspended in the sky over one meridian, as is already currently the case with Pluto and its moon Charon. However, the Sun will become a red giant engulfing the Earth-Moon system long before this occurrence. In a like manner, the lunar surface experiences tides of around 10 centimeters amplitude over 27 days, with two components: a fixed one due to Earth, because they are in synchronous rotation, and a varying component from the Sunday. The Earth-induced component arises from libration, a result of the Moon's orbital eccentricity. If the Moon's orbit were perfectly circular, there would only be solar tides. Libration also changes the angle from which the Moon is seen, allowing a total of about 59% of its surface to be seen from Earth over time. The cumulative effects of stress built up by these tidal forces produces moonquakes. moonquakes are much less common and weaker than are earthquakes, although moonquakes can last for up to an hour, significantly longer than terrestrial quakes because of the absence of water to damp out the seismic vibrations. The existence of moonquakes was an unexpected discovery from seismometers placed on the moon by Apollo astronauts from 1969 through 1972. One of the earliest discovered possible depictions of the moon is a 5,000-year-old rock carving orthostat 47 at North Island. Understanding of the moon's cycles was an early development of astronomy. By the 5th century BC, Babylonian astronomers had recorded the 18-year Saros cycle of lunar eclipses, and Indian astronomers had described the moon's monthly elongation. The Chinese astronomer Shi Shen, 4th century BC, gave instructions for predicting solar and lunar eclipses. Later, the physical form of the moon and the cause of moonlight became understood. The ancient Greek philosopher Anaxagoras, 428 BC, reasoned that the sun and moon were both giant spherical rocks, and that the latter reflected the light of the former. Although the Chinese of the Han Dynasty believed the moon to be energy equated to qi, their radiating influence theory also recognized that the light of the moon was merely a reflection of the sun, and Jing Fang, 78 to 37 BC, noted the sphericity of the moon. In the 2nd century AD, Lucian wrote the novel A True Story, in which the heroes travel to the moon and meet its inhabitants. In 499 AD, the Indian astronomer Aryabhata mentioned in his Aryabhatiya that reflected sunlight is the cause of the shining of the moon. The astronomer and physicist Alhazen, 965 to 1039, found that sunlight was not reflected from the moon like a mirror, but that light was emitted from every part of the moon's sunlit surface in all directions. Shenkuo, 1031 to 1095, of the Song dynasty created an allegory equating the waxing and waning of the moon to a round ball of reflective silver that, when doused with white powder and viewed from the side, would appear to be a crescent. In Aristotle's 384 to 322 BC description of the universe, the moon marked the boundary between the spheres of the mutable elements, earth, water, air and fire, and the imperishable stars of ether, an influential philosophy that would dominate for centuries. However, in the 2nd century BC, Seleucus of Seleucia correctly theorized that tides were due to the attraction of the moon, and that their height depends on the moon's position relative to the sunday. In the same century, Aristarchus computed the size and distance of the moon from Earth, obtaining a value of about 20 times the radius of Earth for the distance. These figures were greatly improved by Ptolemy, 90 to 168 AD. His values of a mean distance of 59 times Earth's radius, and a diameter of 0.292 Earth diameters were close to the correct values of about 60 and 0.273 respectively. Archimedes, 287 to 212 BC, designed a planetarium that could calculate the motions of the moon and other objects in the solar system. During the Middle Ages, before the invention of the telescope, the Moon was increasingly recognized as a sphere, though many believed that it was perfectly smooth. In 1609, Galileo Galilei drew one of the first telescopic drawings of the Moon in his book Sidereus Nuncius and noted that it was not smooth but had mountains and craters. Thomas Harriot had made, but not published, such drawings a few months earlier. Telescopic mapping of the Moon followed. Later, in the 17th century, the efforts of Giovanni Battista Riccioli and Francesco Maria Grimaldi led to the system of naming of lunar features in use today. The more exact 1834-36 Mappa Selenographica of Wilhelm Beer and Johann Heinrich Madler, and their associated 1837 Book der Mond, the first trigonometrically accurate study of lunar features, included the heights of more than 1,000 mountains, and introduced the study of the Moon at accuracies possible in earthly geography. Lunar craters, first noted by Galileo, were thought to be volcanic until the 1870s proposal of Richard Proctor that they were formed by collisions. This view gained support in 1892 from the experimentation of geologist Grove Carl Gilbert, and from comparative studies from 1920 to the 1940s, leading to the development of lunar stratigraphy, which by the 1950s was becoming a new and growing branch of astrogeology.